All right, are we live? Let's see. Let's see. So let me put this up on Twitter. Forgetting to keep this open. So let me put this up on. Okay. Where's? There it is. And so here we are. Welcome and hello. Oh, let me get the right chat. Yeah, welcome and hello. So the deal today is not today. Right now is I'm going to take a look at this maximal squares question. Given a 2D binary matrix filled with zeros and ones, find the largest square containing only ones and return its area. I'll put 4. Okay. So brute force solution is to just go through every possible square and get the. These are squares, not rectangles, so we just need one side length and get the square to the largest length. Excuse me. That would take time cubic with regard to. Oh no. How long would that take? Binary matrix. You would go through. You would go from left to right. It would be, and top to bottom. I want to say this is quintic with not quintic. O of m squared times n squared, something like that, where m is the width and n is the height, or the length and the height, we'll call it width and the height. The reason is that you would have square size 1, left to right, would be m in the for the first row, m times, then 2 would be m minus 1, and then 3 would be m minus 2, etc. So you'd have O of m squared, left to right, in the first row, where m, I guess, is the number of columns. And then each of those squares themselves are of size, the number of times you do that is m times, right, left to right. And that's assuming that m is larger than n. So that's O of m cubed, right? And then you've got to do the same thing on the next, for each row. And that's going to be n O of n rows. It's actually n minus, yeah, O of n rows, right? And you would do this, you would assume, right, and each square is itself m squared. So O of m to the 4th times n, where let's assume m is larger than n. It's the larger of the two. Or alternatively, O of n to the 4th times m. That's the brute force approach. Pretty expensive way to do that. Pretty expensive way. Another approach would be possibly to I guess what you could do is parse the whole. Another approach is maybe to walk through the entire matrix, left to right, top to bottom, right, point by point, and you're going to find the largest square that begins at that point, that includes that point, let's say. So that would be O of n, m times n, And then I guess times the actual largest square, I guess. Now, the thing about that is, wondering if there's any optimization there you can do. That's a little bit better, but it's still like O of m times n times, I guess we'll call it k squared, where k is the largest square possible. Something like that. It's a little bit better than that, but it's at least bounded above by that. That's still kind of expensive, but it's better. And my thinking is, well, can we optimize that? That's what I'm trying to do. I'm looking to do, thinking about what can be done. You excuse me. What can you do? How can you optimize this? And in what way? You're never going to return to that point again. However, the point to the right, down and to the right of that point, if there's a square there, no, it doesn't. No, it doesn't have any effect. Thinking about like if the square encompasses that point, but no, it's not. Doesn't really matter. Wondering if there's a better way to do this. Some way to do this. Largest square containing only ones. I want to maybe employ some kind of divide and conquer algorithm, something like that, possibly. No, it doesn't really. This is an interesting question. I'm kind of stumped. I'm stumped for like a more efficient way to do it. I mean, I could think of like a brute force approach, but I don't know. There's a few things. Like one, I don't know what the bounds are. Like, how big are these matrices that we're dealing with? Ideally, I want to get something that's like O of m by n. You know, you visit everything in the matrix. I guess there's some efficiency upshot if it's a somewhat sparse matrix doing what I described before, but even that is still kind of like. I don't know. I mean, that's like the only thing I could think of. That's all I got. It's offhand. There's got to be a better way to do it than that. That's just the first thing that comes to mind. First thing I think of. I want to do something like a convex hull kind of a thing. Something like that. That you kind of, wean down into a square. Maybe like a bounding box. So you say, okay, there's zeros here, so this bounding box can't be. So you got to remove an edge that has zeros in it. So you move it down to this one. So that has a 0. Well, no, that doesn't really work, does it? Because you could miss it depending on which edge you remove first. This has all 1s. These are 0s. So you could remove these 0s. You look here. But then you'd remove this 0. We want to make a square out of it, right? So you'd have one possible square here. You have like 4 different possible squares you could pick from. And then each of those 4 squares have, so this is not a square, and those 4 have squares you could pick from. Or rather, it's not a full, complete square. So they have 1, 2, 3, 4 squares. And then each of those have 4 subsquares that you could pick from. Each of those, none of those are complete. You could do a backtracking algorithm like that. That's kind of awkward though. Excuse me. Start of the big square, backtrack on those subsquares. I mean, you could do it that way. It's just kind of bad. Square of size 4, and then you have squares of size, the squares of size 5, and the squares of size 4, and then you have squares of size 3. 1, 2, 3. No, this is 1, 2, 3, 4 by 5. 4 by 5. Okay. So you have 4 by 4 squares. 1, 2, 3, 4, and then let's say this 4 by 4. Then you have 3 by 3s. Why does it feel like it's? Oh no, it's not a 4 by 4. This is a 4 by 4. 2 4 by 4s. And my friend's giving me a call. I'll call him back in a bit. Call him back. Right, you have 2 4x4s, excuse me, not a, yeah, 5x4, you only have 2 4x4s. 1, 2, 3, 4, 1, 2, 3, 4. So you have these 2 4x4s. And then within these 4x4s, you could do 3x3s, right? So like this 3x3, and then you have 4 2x2s, 1, 2, 3, 4. Right, and obviously you see you have the 2x2s. You get the 2x2 here. However, among these 2 4x4s, you know, it branches off the tree to a lot of different directions. I'm wondering, something at least interesting you can do. One small optimization, if you do this backtracking kind of idea, is that as soon as you discover something that's a 2x2, then all of the 2x2s can be, you can just stop, you can terminate early. You don't even need to consider, you know, ensuring that it's a full 2x2 and that and then obviously operating on its sub squares, we'll call them. Sort of sub possibilities. I mean, these are reasonable approaches. I mean, these are just things that can be done. It's just, these are all kind of like exhaustive searches though. Like it's kind of expensive to do that, to do what I just described. I don't know how long it would take. I don't even know what the total runtime would be. You can also apply the same thing. Well, that doesn't really matter, does it? Like I want to use the information from things that I've already processed. Somehow you reuse the information. Like if I discover like there's a 1 here, or better, if I discover there's a square here of 4, right? Then there could be a square of like 3 here though, right after it. You know, like there's no, I don't know. Like I don't know how to. Excuse me. Huh. Oh boy. So I've got a backtracking algorithm. I've got some somewhat brute force algorithm. And the nifty thing about the backtracking algorithm is that, right, you can just stop immediately trying to check subarrays. Or subsquares that you've already, basically if you already found that there's a 2x2, then all the other 2x2s don't need to be checked. You can terminate those branches early from that point on, which is kind of neat. It becomes kind of a graph search question, like a breadth first search or a depth first search. But it's still not very good. That's the problem. I'm thinking the sort of brute force approach where you just visit every one and sort of spread out from there to find if there's a square associated with it. I'm thinking that's just optimal. You know, in a sparse graph, it's linear time, and in a dense graph, it's a dense matrix, it's still pretty good. Thank you, guys. I think I'm just gonna go with the kind of brute force-ish question approach. I don't really know. If we time out, that would be unfortunate. But so the way this is going to work is there's going to be a subroutine that's basically going to be like find largest square for a particular point. In this case, we're going to, in this case, we're not going to modify the matrix at all. I was also thinking if there was a way I could modify the matrix, but there really isn't. Like the previous information, I'm not really sure in this algorithm how useful it'll be. So int row, int column, and it's going to be, it's going to return an integer, and it's going to be kind of a while loop, I guess. An outer loop. The inner loop is going to be, basically you're going to add for some int ret. So we'll say just sanity check, or rather we want to say something like this. So we'll say int ret equals 1, and what it's going to start with is oh no, we'll do it this way. For int I, or just r equals row, and R, let's do, I don't know. You're going to create these L shapes, or backwards L shapes from the initial point. So it's going to be there's some row, some column. How do we do this? A single loop. Do the rows, the row and then the column, or the column and then the row and then the column. Yeah, I guess that makes sense. So the row starts off at ret. So actually we'll do, okay, we'll do, all right, I got it. So row starts off at 0, and we'll say increment the row till ret plus 1. So R is less than or equal to ret, and increment the rows. You're going to use ret as the column. So we'll say if matrix of row and column is not equal to 1, that's a character, then we're going to return false. We're going to actually break. We're actually going to do a kind of like a go-to type of deal, or we actually just do sort of bool stop equals false, stop equals true, and then we can also break. And we basically say if not stop. I think I got the right idea here. So if not stop, and we'll do the same thing. Column equals 0, and so we did each row at the ret column, and then we're going to do each column at the ret row. We're actually not going to do the last one. The last column we don't need to touch. Yeah. So. Right. And same thing, we set stop the true and break in all of these cases. And so. And actually, we really want this up here. While not stop, you do this, right? And you say finally at the end, if not stop, then increment ret. Right, that tells you how large the square is. Now there is one more piece to this, which is auto check bounds. Which will say matrix. Actually, we want n rows and columns. if empty or matrix 0 not empty return 0. And we'll say int n rows equals size, and then columns matrix of 0 not size. We're assuming. This is kind of awkward, but yeah, check, and then check bounds is going to be int row, int column. We do also need the matrix here. I don't think we do. Just a return row is greater than or equal to 0, and column is greater than or equal to 0, and row is less than the number of rows, and column is the number less than the number of columns. Right, and we just have to check bounds. Say if check bounds of our ret, and then we'll say if check bounds of ret c. You actually want to do you kind of want to do it like this. Say if you really want to do the other way around. You want to say if not check bounds, or so if check bounds is false, so if check bounds is true, then you want to check this part. If check bounds is false, then you go right here. It's actually how would you do this? If check bounds is true, if not check bounds, then yeah, that's right. That's what I want. This is like a this is kind of interesting. So if this is false, then we go right here. We never enter here. If this is true, then this right. If this whole expression is false, which means that check bounds is true, then we can check here. Right. No, I had the right idea. Pretty nifty. So I have this stop. Stop is false. While not stopping, we're going to run this check bounds. If not stopping, we can increment the ret value to the next. So we have at least 1, and then we would say ret is 1, and then we do the same thing again, and you would increment. That would mean actually increment to 2. That means that it was at least size 2. And I think this works correctly. So we find the largest square, and then now we want to say for int r equals 0, r is less than the number of rows, increment r for int c equals 0, c is the less than the number of columns, increment c, and we'll say int ret equals 0, ret equals standard max of ret, and find largest square of RC, and return ret. And that's it. Something like this. Wrong answer. Wow. No kidding. Seriously. Really? That's not good. That's not good. Does this need access to more than this? I think I did this wrong. No. What do you mean? Let me get something smaller here. Um, 1, 2. Oh, no kidding. Oh, still. That's not right. Really, it would be squared, right? That's what they're looking for. Now, how come row column 0? First check, stop is false. Check bounds, not equal to 1. Break, so it is equal to 1. This doesn't get, you don't get a stop. It's incremented. And then, you know, as soon as you hit a 0, basically, you stop. Why? 1, 2, 3, 4, 5, 6, 7, 8. What is this? Row 1, column 2? Row 1, column 2? Why is this? I should put breakpoints in there. That's kind of neat. Row 1, column 2, I want to say something like this. I mean, I think I already know what this is going to look like. Kind of surprised I didn't program this correctly. That's like kind of simple. 1, it says. Shouldn't be a 1. It should. Where does this fail? Why does this fail? I want to see. How far does this get before it stops? It only gets through the first iteration, right? Because the ret is 1. So it gets to check that 1 is there, but then it doesn't get to these. Oh gosh. Of course. That's why. Oh boy. NR is what we want. And column. Duh. I've made this mistake before. No kidding. It's supposed to be new row and new column. And new row, new column. Oh, duh. That feels bad. That feels bad. No kidding. How did I miss that? It's supposed to be relative, or it's supposed to be offset. Of course. Duh. Duh. Sitting here wondering why, asking why, asking why. Alright, I think we're just gonna go for it. I don't know, man. Oh, hey. Alright. Sweet. Hey! We did it! Man, I also forgot about that. What's that? Where'd that come from? What? Where'd that come from? Who did that? Yeah. Oh, wait. Oh, no. Oh. Oh. It was so good, I was at 80%. Anyway, yeah, so, I mean, that's great. This is kind of an awkward routine I wrote here. I mean, it's okay, I guess. It's not great. I don't know what to say. I mean, it just kind of is what it is. I don't know. Overall, this is okay. Yeah, sure. Shrug, shrug. Alright, so I'm going to end it there. Thank you for watching. It'll probably be the end of streaming for today. I'm going to go head to bed. Probably listen to some music first, get some sleep. Tomorrow morning, I'm going to look to keep programming. Just keep going. Program some more. Just kind of get through as many problems as I can tomorrow. I'm more likely than not going to email the recruiter that I was working with and say, hey, I know we were going to set up a time to interview, relatively soon. Let's hold off on that. Let's interview later. Hopefully a few months from now, possibly a few months from now. I might want to go buy some clothes too, tomorrow or something. I kind of need like pants. Kind of need clothing. Yeah. Maybe, I don't know. Anyway, thank you all for watching. Talk to you soon. Have a good rest of your day. We'll be streaming tomorrow, so take care.